everyone. I'm today's guest lecturer. My name is Matthew Hunter. I'm a now longtime PhD in SLAB, and I'm going to be talking to you guys about fast optimal control using reachable set theory. So looking over what this lecture is going to talk about today, we're going to start with kind of a problem statement of what this work's about and a formulation of the base control problem we're going to be working with. We'll then dive into reachable set theory, which I think you guys have seen once before. I'm not sure where I fall in the order of lectures. But go over that very quickly so we can then dive into closed form solutions for optimal control using ROEs for both impulsive or propulsive control, as well as differential drag control, looking at an application of these techniques on the SwarmX mission. And then we'll look at applying the same sort of optimal control techniques numerically to an arbitrary control problem for impulsive control, and then look at some of the newest work that's being done in the lab right now, which is working on CR3BP relative motion. So looking first, nice. Walter can't be the only funny one. Looking first at the problem statement. So it's going to be a lot of jargon, but we'll dive into it. So the problem statement of this optimal control problem is to achieve a desired relative state over a fixed time horizon or control window with a globally energy optimal impulsive maneuver plan in a linear time variant dynamic system. Now, what do all of these terms mean? Energy optimal means that we're using a minimum quantity of an actuation resource on board, so something like spacecraft propellant, fuel, something that you can't get more of once you're in flight. An impulsive maneuver is an instantaneous change in, well, for our purposes, relative velocity. And this assumption can be made when you're dealing with a maneuver that is relatively short with respect to the variance of the dynamics of the system. For example, the length of a thrust curve of a propulsive maneuver versus the full time or orbital period. Finally, the constraint or the dynamic system that we want to work with is a linear time variant dynamic system, which is an accurate model of the nonlinear dynamics when you choose the right state representation, such as with relative orbital elements. Importantly, a kind of add-on to all of this, we want all the control algorithms that we're deriving and producing to be computationally simple, such that we can put them on board a spacecraft. We already have a whole bunch of algorithms that can be used on ground and they work great, but we want to actually push the bounds on what can be solved autonomously on board to push autonomy in space, reduce the ground component. So looking at the state of the art in this field, we kind of are grouped into 4 different broad sections. We have closed form solutions, which are simple, predictable, computationally efficient. They've got a great deal of flight heritage, but they often are very case-specific in both their applicability and their optimality. And they can only include very limited perturbations. Direct optimization offers a much broader generality in control problem and input variables, but tend to be far more computationally intensive. And unless your problem's convex, you have no optimality guarantees, which, especially for things like keep out ellipsoids and stuff like that, it's often not a convex constraint. For indirect optimization techniques, instead you derive the necessary and sufficient conditions for optimality, but these techniques can also end up being very computationally intensive when you actually apply them within a solver. What we're going to do is we're going to attempt to apply reachable set theory, which can be applied to any linear system, to easily visualize cost optimality and find optimal input times, with the downside of reachable set theory being that it's often difficult to incorporate operational constraints. Effectively, what we're going to try to do is we're going to apply reachable set theory to both closed form solutions, or produce closed form solutions from reachable set theory, as well as direct optimization to make closed form solutions provably optimal, and to make direct optimization far more computationally efficient such that we can use it on board spacecraft. So these are the state and the dynamic system that we're going to be considering as part of the base control problem, a very simple control problem at the end of the day. Looking at an absolute Keplerian orbital elements, which are given as alpha, quasi-non-singular relative orbital elements, which are given as delta alpha, and control inputs are going to be given as delta V or delta V. To formulate dynamics, we're going to use a state transition matrix, which propagates a state from the time t until the end of the control window tf. And a control input matrix B, which translates delta V into direct changes in relative orbital elements. The base kind of instantaneous linear dynamics model we're going to be using is the very standard time rate of change of the ROE equals a plant matrix times some current state plus the control matrix times some current delta V. Instead of just using this instantaneous form, we're then going to discretize the system, which means we're translating maneuvers now not instantaneously, but all the way from the time they happen to the end of the control window. So a state TF set equal to an initial state, propagate across the control window with the STM, and then the delta V's each propagated to the end of the control window. What we can do for simplicity is group the invariance of the control problem into a quantity known as the pseudostate, which is going to be given as delta delta V. And that's taken as the difference between the final desired state at the end of the control window and the initial state propagated across the control window. Nothing that we do with control will ever change these parameters, so we're just going to group them together. So what is the control problem then? We're going to start with an initial chief orbital elements, initial deputy relative orbital elements, and a final desired deputy relative orbital elements. We will then have a reconfiguration control window or horizon, given as the set of times in capital T, which are just the times between the initial time T naught and the final time TF. For the cost function of this, for simplicity, we're just over this presentation going to look at the L2 norm cost function. It's worth noting here that everything I'm going to show you about reachable set theory is applicable to any norm-like cost function. So you could do this for the L1 norm, L infinity norm. You could do this for the sum of norms. So anything that's norm-like will work here, but just to make the presentation simpler, we'll just limit ourselves to the L2 norm since it's fairly broadly applicable to spacecraft. So then the base control problem we're looking at is to minimize a cost C, which is the sum of impulsive maneuvers in the control window, subject to the pseudostate set equal to the effect of those maneuvers in the control window. So now we can dive into reachable set theory. And the idea with reachable set theory is we're going to start with a set of control actions U. These are a bunch of control actions that have a cost no greater than some arbitrary number C that we're just going to use for the purpose of reachable set theory. Again, norm-like cost function. So any maneuver given at a specific time that has a L2 norm of less than C. Moving from the maneuver to pseudostate space, the set S is the set of states that can be reached by any single action at a single time in the control window. So you have the set S here, and then the set of pseudostates, delta delta alpha 1, set equal to be a pseudostate effect of a single maneuver. We can expand this definition of this set S to be the set of any of the times in the control window. So now we have the set of states reached by any, again, still a single action, but now any time in the control window. And so you can see we've expanded down here from times T1 to everything from T1 to T4. And finally, and that's the part where most people get tripped up, so let me know if you have any confusion. The set S star is going to be the set of states achieved by multiple actions of combined cost equal to S at any time in the control window. So we have our set, we have our pseudostates able to be achieved by K maneuvers, an arbitrary number K, in the control window of times in the control window T of maneuvers in that add up to this cost of C. The important thing about this, as you remember, is that we're using a norm-like cost function, or the L2 norm, which means that it scales linearly. So this, in effect, is just a linear combination, which means that we've just defined the definition of the convex hull of maneuvers that can be achieved in the control window. So we can simplify this expression to this, where now we have the set of states within the convex hull or reachable set equal to the set of states that can be achieved with a single maneuver of cost equal to c, scaled by this coefficient, which you can see is just a coefficient constrained between 0 and 1. It's just a percentage. So now we have this linear combination of maneuvers. So now we can take this control problem that we had previously and we can greatly simplify it by actually including the control inputs in the control problem implicitly in the constraints. Now we're just minimizing this cost, C, subject to the desired pseudostate being within the reachable set. Now what does that mean? That means that the reachable set has been scaled by the cost C such that the desired pseudostate is on the boundary. So this is not reachable, that's at optimal cost, and that's at suboptimal cost where the desired pseudostate is actually inside the reachable set. To solve this problem more efficiently, what we can then do is convert this minimization problem to its dual, so from minimize to maximize. And this is important because when we're solving this minimization problem, we're not just trying to throw CVX at it. Effectively, what we have to do is we have to verify for any contour of this convex hull here that the desired pseudostate either lies within the contour or on it. And this can be very quickly computationally intractable if you have a reachable set that has a lot of contours. You got to check them every single time you have an initial guess. Inversely, the maximization problem, you're simply trying to expand the reachable set until it just barely touches the desired pseudostate. And what this means is now you only have to verify that one contour of the reachable set intersects the desired pseudostate. So we've taken this numerically intractable problem, and we've made it far more simple. Now this is going to be a very important quantity here, lambda. I'm going to try to not just say lambda over and over again throughout the presentation. But the idea of lambda is the outward-facing normal of the reachable set. And the optimal choice of lambda is the outward-facing normal of the reachable set that intersects the desired pseudostate at optimal cost. That is a critical component of the reachable set. It's going to give us a lot of information about minimum cost, optimal maneuvering. So that's why this is so important. You'll see why in a bit. Okay, so we have this now easier to solve control problem. Well, how about we make it even easier to solve? Let's make it an unconstrained control problem. Remember that the reachable set scales linearly, so this cost C here can just be popped out, and we can consider a set of unitary cost. Now all we're doing is we're maximizing this cost C subject to C being less than this fraction. Well, that's just maximizing this fraction. So now we can maximize and have a linear fractional program here that is completely unconstrained. And this can be kind of thought of, if intuitively, as the magnitude of the pseudostate here, or the pseudostate projected onto an outward-facing normal of the reachable set lambda, divided by maneuver efficiency in the direction of this outward-facing normal. So by any maneuver in the reachable set. So what does this look like visually? Well, it's a lot clearer to look like visually if we're actually just looking at the maneuvers themselves. So let's expand the denominator of this fraction to the actual definition of what's going on. So if we're maximizing the set of pseudostates in the reachable set for a unitary maneuver, what we're actually doing is we're maximizing over all times in the control window, all maneuvers of unitary cost against this lambda, or outward-facing normal of the reachable set. And the important part about this is that we're effectively identifying what the optimal maneuvers are right here. Because the optimal maneuvers are the ones that act towards this optimal contour of the reachable set. And so we've now boiled down this entire control problem into just needing to find lambda. That's all we need to do to be able to find minimum cost, which is the solution to this equation. And we now know when optimal maneuvers happen, and in what direction they happen as a result of this maximizing T over T, and this maximizing the direction of maneuver of unitary cost. So we have everything we need contained within this problem. Okay, so this is kind of the end of the reachable set theory section. Does anyone have any questions? Because there's confusion here, the rest of it's going to be difficult. Yes?
So we have a few different reachable sets based on the different time step we're at within some control window, right?
Yeah.
So how do we know that if we take some control action at time step 1, how do we know that the reachable step, if like time step 1 was yellow, time step 4 was green, how do we know that the reachable set at time step 4 doesn't change because we took a control action at time step 1?
Part of that is because you're dealing in pseudostate space. It's a linear system, so nothing, there's no nonlinear interactions going on. You're simply just subtracting an effect away, right? The other thing is that what you see here, for these times 1 through 4 here, each one of these are the sets S. You could define them as a reachable set if you wanted to, and you can get subsets of the reachable set. But for the reachable set of the control window, they're all just incorporated in. So if you take a maneuver, nothing, as long as it's optimal, nothing really changes.
What determines the width, or I guess the length of your control window?
You.
And so in theory, if you were to adjust that, does that change the optimal?
Yes, and that's actually something that we use, that can be used in an actual real mission to try to get around difficult to solve reconfigurations or high costing reconfigurations. Like say if you wanted to do a large change in a long track separation, that's going to be really high cost over a very short control window, but you just expand it, it drops significantly in cost, right? So it's a user defined parameter.
So in practice, are you having to optimize over control window sizes?
You could.
You could, but
You could. It's not incorporated into this because the problem that we're considering here is of a fixed control horizon. So that would be a separate problem on top of that. But you're right, there could be 2 steps of optimization going on where you optimize over control window next. Cool. All right. So now we are going to look at closed form solutions through ROEs for impulsive control. To create these closed form solutions, what we're going to do is we're going to visualize the reachable sets numerically by varying all possible maneuver times, maneuver directions, and chief absolute states over, well, varying control window length as well, and taking a sample for each one. We're effectively going to be creating the set S to then be able to find the convex hull. And then we're going to find all possible variations of an outward-facing normal of this convex hull. To do this with ROEs, we're going to split the ROE into 2D planes for ease of visual analysis. And then we can actually identify visually the optimal maneuver candidates that share, well, the contour that defines lambda, right? These are the optimal maneuvers for this given contour. And this we can refer to these contours as dominance cases. And the dominance case is a term for a specific, unique lambda that drives minimum cost. That's named for a related dimension that's driving the minimum cost of the control problem. And for these dominance cases, we can derive an analytical expression for a delta V minima for each one, which is simply the result of this equation, which we'll have all the components of because we're doing this visually. This becomes even more simple doing this in ROEs because we have in-plane, out-of-plane decoupling, where if you look at the control matrix and changes in delta V, in-plane maneuvers will affect only in-plane motion, and out-of-plane maneuvers will affect only out-of-plane motion, at least in the instantaneous sense. What that means is that we can split the 6-dimensional problem into equivalent 4D and 2D problems that are completely decoupled. And so we can deal with radial tangential motion completely separately from normal motion. On top of that, looking at the control matrix, we know that tangential maneuvers are going to be more efficient for in-plane control. So in some sense, we can kind of just neglect radial maneuvers and then just only consider tangential and normal maneuvers for the control window, especially when looking at and figuring out what maneuvers are optimal. Okay, so now let's visualize the in-plane reachable sets. You can see over here on the right where the sets S have been numerically sampled, again by varying all the parameters of the control problem, right? And then you take, using, the MATLAB function, convex hull, the convex hull of these samples, right? And so you get these actually very simple shapes in ROE space for, I will say, near circular orbit. For simplicity, I guess I forgot to mention before, I'm going to be looking at near circular orbit. There's a lot of added complexity and mechanics when you start getting into eccentric orbits, which you can read up on, but I really don't want to have to deal with diving into all of that. And I feel like it kind of takes away from the base understanding of what's going on. So for our purposes, we're going to deal with near circular orbit today, and it's really simple shapes. So what are then the dominance cases of the system? Well, we have a clearly defined parallelogram in the delta A, delta lambda plane, and we have a clearly defined perfect circle in the relative eccentricity plane. So how do we define, say, the optimal maneuvers in the delta V minima for a dominance case? Let's look at it for delta A. So for the delta A dominance case, I kind of have it omitted here, but it's both the horizontal part of the parallelogram on the top and the bottom. You can see that the set S, all the maneuver samples, actually completely share that boundary with the boundary of the convex hull, which means that an optimal maneuver can actually occur at any time throughout the control window. There's no gaps there. As we said previously, for optimal maneuvering, optimal maneuvers are going to be tangential, and the sign is going to be the sign in the direction of the delta A pseudostate. So to find a delta B minima for this dominance case, we know what lambda is, the outward facing normal, it's just up. And we know what the optimal maneuvers are. We can arbitrarily take a positive tangential maneuver at T naught. And through this multiplication and the fact that we have analytical expressions for this STM and for this control matrix, we can find an analytical expression of what the delta V minima is for a delta A dominant control problem. And we can do this for all the dominance cases for in-plane control. So for a delta lambda dominance case, those are going to be the sides of the parallelogram. This is a far more restrictive case. You can see that the maneuver samples S only intersect the convex hull at 2 points, right at the beginning and right at the end. So the optimal maneuvers only occur at the beginning and the end of the control window. That's it. Direction is again tangential, and sign depends on the sign of the delta lambda pseudostate. And we can again come up with an analytical expression of what the delta V minima looks like for this dominance case. The same thing for the delta E dominance case. We have a perfect circle here because of the periodic motion of the relative eccentricity vector. What that means is that an optimal maneuver actually occurs twice per orbit. Once directly at the angle of the delta E pseudostate, and once directly opposite. So you're either taking a positive maneuver or a negative maneuver. Again, tangential, and we can come up with an expression for a delta V minima. It's worth noting here as well, I don't know. I think this is really cool. This is a factor of me discretizing maneuver directions, maneuver times, and all that. In reality, this ball is completely covered. There's no space here, but this looked cool, so I kept it. Okay, out of plane. We only have one dominance case, which is great. It's the delta I dominance case because, again, we have, well, as I found later, it's not a perfect circle, but it's basically a perfect circle for short control windows. So optimal times, again, occur twice per orbit, happening directly towards the delta I pseudostate. Optimal directions are now normal because this is out of plane control. And the optimal sign is positive or negative depending on location. We have this closed form analytical expression. And even better, the optimal maneuvers act directly towards this desired pseudostate, which means that we already know what the optimal maneuver plan is for out of plane control. Simply a single maneuver that acts directly towards the pseudostate. So in many ways, for out-of-plane control, we're done. And that's kind of reflected in what the general mechanics of finding closed form solutions are in both the in-plane and out-of-plane case. For the out-of-plane case, it's very simple. You just find the optimal maneuver time for the out-of-plane maneuver, and you set a maneuver that acts directly towards the desired pseudostate at the delta V minima of the control problem, and you're done. In-plane is not that simple. You're dealing with a four-dimensional state with three different dominance cases. So to solve this problem, we're first going to determine the in-plane dominance place of the actual reconfiguration control problem. And to do this, we're effectively going to do that maximization problem by hand. We know what all possible variations of lambda can be, so we're just going to check all of them and maximize it. The largest one is the dominance case of the control problem. We're then going to find optimal maneuver times, find the effect of maneuvers at these maneuver times, iterate through all potential maneuver candidates and solve a system of equations, to then find an in-plane maneuver plan with lowest cost. And I will go into the mechanics of this. So, finding a maneuver plan. The really cool thing about, especially in the near circular case, in-plane control, you notice, as I mentioned before, that you can do a delta A dominant optimal maneuver at any time in the control window. And you can do a delta E dominant maneuver a lot of times in a control window, twice per orbit. So why don't we just restrict the optimal maneuvers that we're considering to either towards or away from the delta E pseudostate? That means that we've effectively just reduced the problem from 4 dimensions to 3 dimensions. And we can solve maneuver magnitudes using a linear system of equations. So that's how we find the maneuver magnitudes for this control problem. We come up with linear systems that have an optimality constraint, which is that series of ones, and then non-dominant pseudostates, or pseudostates that are not part of the dominance case, right? We're going to scale those non-dominant pseudostates by the delta V minimum of the control problem. So then these C's that we're solving for over here are effectively just coefficients. Again, coefficients of the minimum cost of the control problem. And that's where the optimality constraint comes from as well. It's not guaranteed for, any choice of 3 maneuver times that they're going to be optimal. So for robustness, we also have a suboptimal plan here that we can solve if an optimal solution is not possible at these 3 times. Or if we're delta lambda dominant. Now, delta lambda dominant, as you noticed, only has really 2 optimal maneuver times, and they don't play nice. So we're going to just kind of ignore it. I've addressed this in some of my other work where I'd solve a problem that's delta lambda dominant early and just add delta lambda dominant maneuvers until it's not anymore, and then solve a mostly optimal system. But for the purposes of this presentation, we're just going to ignore it and just get the best possible plan. So here's an example of what this looks like for in-plane maneuvering for a real-world example. So we have this 30-orbit reconfiguration with a desired pseudostate there at the top. And we're going to do in-plane control. So we're going to start with finding the in-plane dominance case. That did not translate well, but that's okay. We have these analytical expressions of the delta V minima, and we're going to solve all of them, and we find that the largest one is the one for the delta E dominance case. So the problem is delta E dominant. We're then going to find the optimal maneuver locations or maneuver times associated with this dominance case or with delta E dominant maneuvering in general. We have analytical expressions for when those maneuvers occur. So we're going to find the angle of the relative eccentricity vector pseudostate and then just solve for those times. We find the effects of maneuvers at the optimal maneuver locations. So for every time that we have found, we're going to be finding the resulting pseudostate that happens when you take a tangential maneuver of magnitude delta V min. And then we're going to iterate through every single 3 maneuver combination that Every single 3 maneuver combination that comes with these series of maneuver times, check to see if they can form an optimal system. If they can't, we're going to solve them suboptimally and find the plane of lowest cost, which you can see here. I think Microsoft Online does not play well with equations, unfortunately, which I wish I had known. But these effectively sum to 1. So we found an optimal system, or found an optimal series of times and maneuver direction associated with this system. We can then create an in-plane maneuver plan with lowest cost at those times with those maneuver magnitude coefficients on the delta V minima, and we end with delta V's. So that is kind of the procedure of how you can find closed form solutions optimally for both in-plane and, as I said, very simply for out-of-plane. Do we have any questions about impulsive control?
So just to confirm my understanding, so the norm of this resulting vector will be the same as the delta V min?
Yep.
Okay.
Sum together.
Okay.
Cool. All right. So now we have closed form solutions for impulsive control. We can now create closed form solutions for differential drag control. Differential drag is simply the difference in atmospheric drag between two spacecraft. So if you have one spacecraft traveling to the left, you're going to have some sort of atmospheric density that pushes it back to the right against the direction of travel. Using a pair of spacecraft, or 3 spacecraft in the case of SwarmX, what that means is that you can place a chief spacecraft as some sort of intermediate drag configuration, and then place a deputy spacecraft at either maximum drag or minimum drag to create a positive or negative relative acceleration between the spacecraft. And the kind of force model that we're going to be using here is given here, where we have a very standard force of drag equation up there, assuming near circular orbit, assuming orbit averaged atmospheric density, assuming that the force is completely tangential in the Chief's RTN frame. And also, as I've been called out a couple of different times at conferences, assuming that the relative velocity between the spacecraft and the atmosphere is the spacecraft's actual just velocity in near circular orbit. And so what this means is that we can drive actually a very simple control force, U drag, which is simply the difference atmospheric drag between the chief and deputy, which is then controlled simply as a function of this differential ballistic coefficient, or the ballistic coefficient is a function of the cross-sectional area of the spacecraft, or in this case, the difference in the cross-sectional area between the two spacecraft. And you can see here that this is actually an augmented differential ballistic coefficient, where we've just captured rho with the atmospheric density within it as well. Now, this is great because now we have a control force that costs nothing. We're kind of assuming, well, with the spacecraft we're using for SwarmX, we know, but in general, spacecraft can usually control their own attitude without using any delta V. So this is effectively just free maneuvering, which means we can introduce a concept called hybrid control, which will be kind of touched at various times and dived more into at different points. But effectively, hybrid control, the goal is to optimally combine differential drag and propulsive control to decrease delta V for large reconfigurations over extended control windows. We can do this by solving differential drag control, figuring out what differential drag's effect is going to be, and then solving a reduced propulsive control problem. And thereby reducing the propulsive cost, assuming we've done this optimally. We can then create a hybrid control problem that's simply an augmented version of the control problem we had before, where we have all the same parameters as before, but now we have this drag control force, and we can simply append this drag control force to the dynamic constraint. by dividing the control window into m time steps and analytically integrating the effect of differential drag over each time step. Differential drag is not an impulsive maneuver. It actually has a very low maneuver magnitude that really only becomes applicable when you're dealing with relatively long control windows. So you kind of have to integrate its effect to be able to fully capture what it does. So now we're going to do basically the same thing as before to create closed form solutions. We're going to visualize every possible differential drag maneuver that can exist in a control window. Varying start times and durations of single maneuvers, maneuver directions, and chief absolute states. Again, the important thing here is differential drag is a zero cost maneuver, which means it doesn't actually introduce any cost to the control problem whatsoever. Which means its optimal policy is bang bang control, but then also the dominance cases are just the same as propulsive control because there's no additional cost being added here. So we can actually take these variations in lambda, or the outward normal of the reachable set, and just apply them to the differential drag reachable sets to find the optimal differential ballistic profile associated with each case. So then we're going to do that. We're going to identify these dominance case differential drag profiles. Differential drag is also an in-plane maneuver, which means we can just get rid of and ignore out of plane. This keynote here, we'll get to more towards the end, but optimal differential drag may result in different dominance cases with equal delta V min. And you'll see what I mean as I dive into the reachable sets. Okay, hybrid reachable sets. We have the propulsive reachable sets and their dominance cases shown on the top row here. And now we visualize the differential drag reachable sets down here. We can see that the shape, actually, in the relative eccentricity vector pseudostate plane is exactly the same. It's a circle. We get a far more nonlinear shape in the delta A, delta lambda plane, but that's okay. We're just going to apply the lambdas, the outward facing normals of the reachable set that we had before, and apply it to this reachable set. So let's do that. What do we find? For the delta A dominance case, straight up or straight down, this corresponds with a maneuver that spans the entirety of the control window. You can see that it just goes straight from the origin all the way up. So this is a very simple maneuver, either completely positive or completely negative over the entire control window for a differential ballistic coefficient profile. For delta lambda, it's actually a kind of similar result to what we see for propulsive control, where the the reachable set on that contour is formed by a contour of maneuver right at the beginning and right at the end of the control window, and there's really nothing happening in between. And so we have these differential ballistic coefficient profiles that span the first half and the second half of the control window, and the direction depends on the direction of the delta lambda pseudostate. For the relative eccentricity vector, what's interesting is that we have a circle kind of forming, and you can achieve the relative eccentricity vector is kind of misleading. You actually get what looks to be a fairly small circle in pseudostate space here relative. I know it doesn't scale here, but it turns out to be really small. And partly why that is because when you're taking these reachable sets, you're scaling a single maneuver, right? Well, it turns out that for the relative eccentricity vector, it's actually this kind of oscillation that happens throughout the control window, and that happens over the course of one orbit. So you effectively have this oscillation that repeats once in orbit. And when you're actually deriving the reachable set, it doesn't capture that. It only captures one oscillation. But then if you know what that cycle is that points differential drag maneuvering directly towards the delta E pseudostate, you can then just expand this profile out to the full length of the control window. All right. As I mentioned before, the full reconfiguration problem, solving it optimally may require multiple of these profiles. And you can kind of see this if I go back here. So we have these broad spans of the reachable set here that we've not defined whatsoever. It's actually happening in those areas if the desired pseudostate intersects that part of the reachable set. That means the delta A dominance case delta V minimum, the delta lambda dominance case delta V minimum have the exact same value. They're equal. What this means that just using the delta A profile or the delta lambda profile is not going to be sufficient to optimally solve the problem. Effectively, say you start with a delta A dominant problem. You apply the entire delta A dominant profile to it, and the resulting problem is now delta lambda dominant. You've applied so much differential drag and you drop the cost of this dominance case so much, delta lambda is now way larger than delta A as far as delta V minima are concerned. That means you haven't actually applied the optimal profile. You just applied the profile for this dominance case. There needs to be a mixture. So that effectively is what the closed form solutions try to do, and that's the most important thing to get from this, is to balance how much of each profile is used to be able to come up with an optimal profile. As kind of the mechanics of this, you start with just the delta A profile, and then you apply or replace portions of the profile with the delta lambda profile and the delta E profile until their costs are equal or you've effectively found the optimal cost. If you happen to overshoot, which is a problem, if you're using a control window long enough, you might actually end up with negative delta V minima. You can then reduce the amount of profile remaining that has overshoot. The mechanics of this, if this is confusing, the exact mechanics of this don't matter as much as you understand that you are simply balancing the effect differential drag has on each dominance case delta V minima, effectively trying to converge almost in a convex way to the single optimal cost of this hybrid control problem. All right, the next slide is kind of a slightly different topic but in the same area. Does anyone have any questions on this? Differential drag stuff.
Operationally, what does this look like when you're actually, applying a differential drag in orbit? Because I imagine it's not an instantaneous, attitude change to go from your full drag configuration to your minimum drag configuration. So how well can you achieve this something approximating this profile in a real mission?
So one of the things I skipped over, one of the assumptions for atmospheric drag as well is that we have a kind of instantaneous change in attitude, because the change in attitude is actually fairly quick with reaction wheels and with small spacecraft. We're not trying to turn the Hubble telescope. We're just trying to turn a CubeSat. So it happens fairly quickly over the span of an orbital period. We haven't done much sims yet for SwarmX to figure out how good of an assumption that is. But not doing that would fundamentally change the control problem in a lot of ways that you could then solve on the back end, but it wouldn't be solving it optimally as simply as this, right?
Kind of along those same lines, if you have requirements for your attitude profile, is that a constraint that you could add in here pretty easily that then just blocks out certain?
Yeah, so one of the plugins or user-defined parameters of the control problem is what is your maximum differential ballistic coefficient. So if you have operational parameters, ADCS can then tell you, hey, this is the most variance we can do. And so then you just solve for that control period differential drag with this variance. And that's how we're going to handle it for SwarmX. There's there's most likely a smarter way to do it, but this is the simplest way to do it that we could think of.
I think you mentioned earlier that you're assuming that the solution takes a bang-bang profile.
Yeah.
How do you know that there are no singular arcs?
What do you mean?
Like, how do you know that there are no periods over which the optimal profile falls between delta B max and delta B min?
So if you do this numerically, it does. But this is where it starts to dive into the difference between hybrid control and differential drag only control. You can kind of see this. I think I included it in my backup. Let me see. Where I actually validated the differential. Yeah, here we go. So this was when I initially published this material. This was the validation I did on the different differential drag profiles. You can see that delta A dominant case and delta E dominant case are exactly the same. But you're right, for the delta lambda dominant and for drag only control, there is some, in between values that are found by CVX. But when you actually look at the effect that has on the delta V's, it's below 1%. So it really, for our purposes, doesn't matter. We're already struggling with the atmospheric density estimation enough that this is fine.
This almost reminds me of like atmospheric entry.
Mm-hmm.
Like you'll see like similar like very strange profiles on like atmospheric entry trajectory optimization.
Yeah.
So.
This actually, and that's another benefit of doing this in a closed form way, is that we don't have these kind of very numerical profiles happening. Like to your point about the changing of the attitude, yeah, it's fairly instantaneous, but we don't want to be doing it that often. So if we have something more like this is not really realizable in an effective sense for a fairly cheap CubeSat like we're going to be using for SwarmX. All right. So one more quick thing about differential drag that I kind of touched on before, but is applicable for actually using it in a mission. The reason why a lot of missions don't use differential drag is because it really suffers from poor control accuracy. The atmospheric density models that we have access to as part of the state of the art are only really reliable within an order of magnitude, which is not great. So the way we're going to address this on SwarmX is we're going to apply Lyapunov stability to have a provably Lyapunov stable maneuver plan. We can actually build Lyapunov function off of this definition of the delta V minima that we derived before by simply just taking the numerator. We know that it has to be positive definite for a control problem that isn't just arbitrary. And so to figure out Lyapunov stability, we just need to verify that this time variant change in the Lyapunov function V is less than or equal to 0. We know that this must be positive, which means we need to constrain this to be negative. What is the time rate of change of the pseudostate? That's just a maneuver. So that's what we do here. We have the time rate of change of the pseudostate set equal to the effect of a maneuver, and then we're going to add in some error. We'll just say some arbitrary error epsilon. And what we can kind of trivially see is if the magnitude of this error is lower than the actual maneuver realized by the physical system, we have Lyapunov stable system. How do we apply this? Here's kind of visualization of what this looks like in pseudostate space. So we have our stable convergence bound on the top, and this green maneuver here is the maneuver that the system is actually executing. So this is what is happening in real ground truth space. We have lambda, which is the optimal lambda for the reconfiguration problem. And so we can think of like, well, let's say, it's a differential drag maneuver, it's tangential only. What if we underestimate its effect? What if we model it as being too low on board? It falls in this area, right? Which is great. That means that we've modeled an effect to have a certain, or model maneuver to have a certain effect, and we've actually done better. What if we have a maneuver that's over here? That means that we've overestimated the maneuver that's going to be accomplished. That's okay too. We're still moving in the direction that we want to move. Where it starts to become not okay is when that error becomes greater than the effect initially realized by the maneuver. That is where this convergence property comes from. And on Swarm X, the way we're going to deal with this is that we simply just always guess low. So as long as you can just basically guarantee that you're maneuvering, the maneuvers that you model are going to be less than the effect that they actually achieve, you have a convergent system, and therefore you kind of deal with this atmospheric estimation issue. Does anyone have any questions about this before I dive into Swarm X?
I'll introduce the Apple of control next week.
Cool. Yeah, I wasn't sure where it fell. All right. So the project that I've spent most of my time working on is the Swarm X mission while here in SLAB. And Swarm X is going to be a novel 3 CubeSat autonomous formation flight mission doing distributed aeronomy, which means that we have a science objective of improving understanding of these fancy words that effectively mean space weather. We're also going to be doing atmospheric density, or Shane, I should say, one of my lab mates is going to be doing atmospheric density estimation through relative accelerometry. And yeah, space weather modeling. Engineering objective, as you might guess, formation flight, formation acquisition and maintenance for more than 2 spacecraft, and applying these novel hybrid control algorithms. The big thing about Swarm X, and the reason why we're so interested in differential drag, is this, which is kind of the different configurations we're looking at for a swarm in Swarm X. You can see that when we are actually taking data between the 3 Swarm X spacecraft, we're separated by 1,300 kilometers. Instrument calibration has to happen on the range of 10 kilometers. And you can't do that with onboard fuel alone. It would take forever. So this is why we're so interested in using differential drag, is to decrease and increase the tangential separation without needing to put up a prohibitive amount of fuel. So for the flight code demonstration, I'm going to be looking at software-in-the-loop simulation of the full 3-satellite swarm with controls solved autonomously on board. For Swarm X, we're using a kind of not fully naive, but fairly simple model predictive control periodic maneuver replanning setup where we just, throughout the control window, replan the entire maneuver plan from where we currently are. Propulsive maneuvers are being split into chunks to fit the propulsive requirements. The situation is that we're going to have a ground command to initiate a tangential swarm contraction from wherever it is at 20 kilometers of tangential separation down to 5 kilometers of separation. The orbital environment is going to be considering J2 and atmospheric drag, and uncertainty is going to primarily take the form of expected onboard state estimation performance. So we're going to be rejecting that, as well as in an accurate atmospheric density model. We're going to be using Harris-Priester on board, whereas the ground truth is NRLM size. So if we look at this reconfiguration using the flight code for propulsive only control, we can see that we actually, we achieve our desired state by the end of the control window. I set the control window for this reconfiguration at 500 hours, which is about 320 orbits. And so we start at these initial states at the beginning here, and we converge to this desired state by the end of the control window. We see, primarily, I think, not too unexpected behavior, but the big thing here is that even at 500 hours, we're looking at a lot of delta V. And this is even restricted to just in-plane delta V for both Deputy 1 and Deputy 2. And that's kind of a prohibitive cost of maneuver to be conducting just to move 15 kilometers over a fairly long time span. Well, what happens when we apply hybrid control? It drops the total delta V cost of the reconfiguration precipitously. We're looking at, that's almost nothing compared to what we had before. And the kind of fun thing is you can actually see differential drag kind of happening and fixing itself throughout the control window, because I have a On this, I have control resolving itself about every 5 orbits or something like that. And so you can see this modulation of the differential ballistic coefficient going on as it just oscillates back and forth trying to converge to a final state. You can even see Deputy 1 doing a fairly terrible job at what it does and not getting there. So at the end it goes, oh no, I didn't get there, and just shoots up in an attempt to finally get to the desired state, which it kind of does, but now it's off there in the middle of nowhere. So that's not great. Obviously that would get fixed over more control windows, over a larger time span, but just looking at this in isolation, that's what we've got. It's even cooler, at least to me, because we can do this with differential drag alone. It actually happens faster than the control window that we've defined. And it happens at no delta V cost. We can just do this. And we can see the large variations or changes in delta A happening because of differential drag control. So you can clearly see the effect of these profiles kind of outlined here. The other cool thing is we can actually almost see like a underdamped response going on here, which is kind of what we expect, right? Because we've limited the modeled onboard differential drag control to be less than that's actually being realized. So in effect, we're just overshooting every single time we do a maneuver, which is exactly what we find here for delta lambda. Yeah. Anyone have any questions about this?
Just so I fully understand, is this still essentially using, or is the control input here still bang bang control, and this is the change in cinema jacks, or?
It's still bang bang control, yeah.
Okay.
We have not yet produced a high fidelity enough simulation to actually account for attitude.
Okay.
Yet.
How does the hybrid reconfiguration decide when to use between differential propulsive? Like, couldn't it just decide to do differential if it's faster and uses less delta V?
Well, there's a couple different ways to answer that. One is that if the system is kind of constrained to use the control that it's given. So in this sense, I've told SwarmX to use hybrid control, so it's going to use both differential drag and propulsive control. And actually, part of the reason why this system is convergent is that it's only resolving the differential drag maneuver plan. The original propulsive plan that it starts with, it does not change, because if you change it, propulsion starts wanting to take in the errors and add cost to fix those errors, and we don't want that. So we're actually accomplishing this error rejection using differential drag modulation alone. I think that answers it.
I guess you don't have the profiles here of the control inputs.
I figured they'd take up too much space.
I could have been added on top of the plots. But so in the previous slide, you have impassive, so propulsive control only. Can you show that slide again? And that works. Well, it converges with some cost. Then with differential drag control alone, that also provides satisfactory results.
Yeah.
You have a very small delta. So what happens in the middle when you have the hybrid? Because so in your process, do you first solve propulsive, and then you use differential drag to correct?
So the way SwarmX is ordered is kind of the way I showed the hybrid slide to begin with. It goes differential drag and then actually out of plane control, in plane control, because there's some coupling fixes going on there. First differential drag control. Yeah. The reason why this is doing this is because I'm not showing it, but it's actually solving the full 6-dimensional ROE state. And so there is some relative eccentricity vector control going on. And what happens over the course of the control window is that for delta lambda controller actually ends up being a singularity at a time duration of 0, right? Because you're using a tangential only maneuver, it's adjusting delta A to try to accomplish a change, in delta lambda. So as you get closer and closer and closer, it shoots up. But it doesn't necessarily shoot up until it gets right to the end of the control window. So what's happening here, and the reason you see these oscillations, is because it's actually doing primarily the delta E dominant maneuver plan for portions of this entire time until it gets here and it realizes that it's screwed up. And that's when it says, okay, screw the relative eccentricity vector, I'm just going to fix delta lambda, because that delta V minima shoots up as you get to the end of the control window. Cool. All right. So finally, and far more abstractly, we're going to look at reachable set theory doing numerical optimization for an arbitrary problem for impulsive control. So taking hybrid control, throwing that out of your head, we're now just doing impulsive only control again. To create a numerical solver, what we're going to want to do is we're going to reformulate the control problem to be solved by direct methods. Effectively, we're going to solve for lambda using convex optimization. To do that, we're going to convert this unconstrained maneuver or this unconstrained control problem we've been working with, and we're going to convert it into a second order cone program that can be solved more simply numerically. We're then going to derive analytical conditions and evaluations for optimal maneuvering that can be done very efficiently. And as I said before, solve it with convex optimization, which is more efficient than applying direct methods alone to the control problem. So how do we do this conversion? Well, we start from a linear fractional program, and we end up with what is a fairly standard in the literature conversion from a linear fractional program to a second order cone program here, where this number 1 here is kind of chosen relatively arbitrarily, but because it's simple. The important thing about this is that we have this constraint over here, and we can actually evaluate this constraint analytically for a given choice of lambda without needing to sample through all of the delta V's. We can evaluate it through the Cauchy-Schwarz inequality as just this quantity, which is a known, and something we're optimizing for, and just taking the L2 norm of it. So then for a numerical algorithm, the algorithm proceeds in basically 3 steps. You initialize by taking an initial guess of lambda, or the outward-facing normal of the reachable set, as the direction of the desired pseudostate. You then find the most optimal subset of maneuver times for this choice of lambda. You're then going to iteratively refine both the choice of lambda and the subset of optimal maneuver times, starting by finding a new optimal lambda for the set of times t, and then using that lambda to find a new optimal set of maneuver times, and going back and forth and repeating this until you converge. You can then use a quadratic program to extract the optimal maneuver magnitudes at these times and directions. So for a visualization of this, what does this actually look like, or what's happening in practice? So for initialization, we're setting our initial estimate of lambda in the direction of a desired pseudostate. And that's what's happening here. We have the desired pseudostate, lambda's pointing that way. We're going to discretize the control window using a spacing delta t. Here, we're just going to assume that gives us these 4 times that we are operating with. And then we're going to find the most optimal subset of maneuver locations for this choice of lambda. Again, remember, we have an analytical expression of this evaluation. So we're just going to take every t that we have, and we're going to find what that expression evaluates to, and take the n highest. In this case, let's say n equals 3. So we know that for maneuvers happening at these 4 times, t1, t2, and t3 have maneuvers that act most in the direction of lambda. You can see T4 here is far more restricted, far further away. And so this is our initialization. So, iterative refinement. We're then going to solve the second order cone program over and over again until we converge. So we take this subset of times, say the T1, T2, T3 that we started with. We're going to solve this program using CVX. That's going to give us a new lambda. Using that lambda, we can then step through all of the times again and come up with a new subset of optimal maneuver times. We remove times from that set if they're below some tolerance set by the user, epsilon removed. We add t's from the control window if they're greater than this constraint at the end here. We're going to continue this until the highest evaluation over all these times is less than or equal 1 plus epsilon cost, which is epsilon cost is another user-defined parameter. So what does this look like for this two-dimensional problem we've got? We optimize lambda for the subset of times. What's interesting about this is that two of the maneuver times we saw for previously actually are on this optimal boundary of the reachable set. So we just find lambda, first try. Now we're going to pass through all the maneuver times. We know that we have optimal maneuvers here, but at T1, I think it's T1. Is it T1? It is T1. At T1, it doesn't actually touch the optimal contour of the boundary of the reachable set. So it's removed. T4 does. So now we have an optimal maneuvering happening at T4. And effectively, this problem was solved in one iteration with one single refinement of lambda. So now we're going to do control input extraction, which I know this is a big new equation that hasn't been shown at all previously, but we're effectively just trying to minimize the square of the error for all of the optimal maneuver times that we have in our optimal set. The interesting thing about this is that if you have your optimal maneuver plan may not be unique. Given previously that we have 3 optimal maneuvers, all that can reach this boundary of the convex hull, combining these maneuver directions into a maneuver plan here in green and these maneuver directions into a maneuver plan here in green are equivalent. They're both going to reach the desired pseudostate at optimal cost. So just because you solve this problem numerically doesn't mean you found the only solution. So how can this problem, or how can this solver be used? Well, we're currently using it for some of the newest, yes?
Sorry. Just so I fully understand, how do you know that this iterative conversions, converges?
We don't.
Okay. There's no
There's no formal proof that it will converge. In the initial paper that Adam did, there's no formal proof that he gives. He used a Monte Carlo analysis, at least not in the...
It's guaranteed to converge within a tolerant prescribed by the user.
Oh, is there one later?
Yeah.
Oh. Okay. It does.
Okay,
It's guaranteed.
In one of his initial papers, he says we offer no formal proof of convergence. That's when I remember.
I think because it's just by inspection of the property of the convex hull.
Okay.
So I think it's trivial to show that it's globally convergent.
Okay. Can it not be modeled with the maybe not, but the optimal times as an optimization variable as well in the SOCP? So it's not without iteration, or
Well, the times are solved here as part of the problem. That's the difference with the standard CVX.
okay.
It's the key advantage of this method. We are solving for the maneuver times.
So,
which
for
is a
example, CVX would solve for a maneuver, like if you just apply it to the base control problem, you'd have to optimize every single maneuver time of your discretized set, right, in one go. Whereas this is doing an iteration of a much smaller set of maneuver times that can solve that problem far more quickly. and then we don't need a numerical algorithm to be able to evaluate this. We can just pass through all the times and then do it again. Yeah, I should have paused for questions here. Yeah.
Okay.
Are there any other questions about the numerical algorithm? I should have paused here. Apologize. Cool. All right. Rather quickly. All right.
Students might ask, why do we use a numerical optimization if we have the possibility to solve it in closed form?
So there's a couple reasons why. One is that the problem that you're considering may not be conditioned well to result in closed form solutions. We have the advantage of using ROEs that results in very simple shapes in the reachable sets, which means that we don't have to derive a whole lot of variations of lambda, but that's not always the case. In fact, like part of the reason we have papers on this is because we've chosen ROEs in contrast with, say, like RTN motion propagated by the HCW equations. That is not nearly as plays as nice. So that's part of the reason why. The other reason why is that not all situations, even within that, can be solved optimally. This is the numerical algorithm will always result in the optimal solution to the reconfiguration. But as you saw before, when coming up with in-plane maneuvers for impulsive control, we do the best we can, and we work with the situations that we can. But like for the delta lambda dominance case, there just is no way in closed form to come up with an optimal maneuver profile for that with the techniques that we currently have available.
So a very practical example is closed form solutions are derived based on a certain knowledge of the contour of the convex hull, so of the reachable set. But this changes depending on the length of the reconfiguration time or of the control window. And if the system, the dynamic is periodic. And so if you notice when we show the reachable sets for the relative eccentricity, relative inclination vector, they complete a full circle because maneuvers can occur at any time during the orbit. But if your reconfiguration time interval was, for example, half an orbit, then it's just only a fraction of that reachable set. And so you will have to resolve analytically the problem because now you have a different shape for your reachable set. So that's the drawback of the closed form solution. So you derive them for a certain geometry of the reachable set, which, however, changes with the length of the control window. Instead, a numerical optimization algorithm, which is guaranteed to converge within a tolerance prescribed by the user, can work with sub-orbital reconfiguration. So that's one of the key reasons why we have a numerical method, because it's general.
Yep. All right. Rather quickly. So this work that I'm doing here is kind of a collaboration with Walter. So we're going to reuse a couple of his slides here just for simplicity and because it looks familiar to you guys. The work that we're considering is relative motion in the CR3BP. So if we have absolute motion of the chief defined in a moon-centered synodic frame, we're going to be looking at the relative motion of a deputy spacecraft with respect to a chief in the LVLH frame, which is analogous in some ways to RTN, or at least in the ways that I plotted. And so Walter showed you guys as well a kind of derivation of the CR3BP relative dynamics in this LVLH frame, where you start with this state that is the range from the chief over the time rate of change of the range from the chief, and you end up with this kind of change in state equals a plant matrix times a current state. But as I mentioned before at the beginning, this is not really, the plant matrix is not sufficient to be able to solve impulsive control reachable set theory. We need to be able to propagate maneuver times from the time they happen to the end of the control window. We need an STM. How do we get an STM? Well, we can do it efficiently or inefficiently. So, efficiently, at least ideally, one of the techniques that we're using currently is using a matrix exponential approach. When you take a matrix exponential of a plant matrix, you result in an STM. But the problem with this STM is that it is linear time invariant, is the definition that you've created. And we want linear time variant because this is CR3BP. It's highly varying dynamics. So what we're going to do is we're actually just going to stack linear time variant STMs over short time periods to capture this time variance and get a linear time variant STM. In contrast with that, we can just say, well, we're going to throw some numbers at it, numerically integrate it. We know how the STM changes over time. It's simply the plant matrix. And so we just simply numerically integrate it where the initial choice of the STM is just the identity matrix, because at the beginning, there's no change going on from the initial state. But the idea of this is far more computationally intensive, so we don't want to do it. So the two examples we've been working with for our current work, we first have a simulation occurring far from Paraloon, where Paraloon is the closest point in the Chief's trajectory to the moon where the most nonlinearity or most highly varying happens. And so for control far from Paraloon, you can actually see no control, rather smooth curved trajectory here, as well as the control trajectories using both the matrix exponential STM approach as well as the numerical integration approach. They both come up with very similar maneuver plans. They both come up with fairly smooth trajectories. They both basically achieve the final desired state. And if you look at their runtimes, the computational advantage here of the matrix exponential approach is obvious. But this is for a fairly well-behaved system that we have this matrix exponential approach accurately characterizing the dynamics. What if we don't? What if we're near Paraloon? What if the Chief is just kind of doing what it wants? Because we see here we have a kind of uncontrolled trajectory that is very nonlinear, and in this use case we want to control the deputy to stay relatively close to the Chief. So we do in this kind of blown up version here. And we can see that the matrix exponential approach still kind of offers this runtime savings, but this comes at a cost of control accuracy. It's fairly similar maneuver plans, but it doesn't accurately achieve the final state at the same final state accuracy. So this is kind of a way we've been using the solver in the lab to address a new problem that hopefully is still fairly familiar to you guys. Yeah, does anyone have any questions on this fairly quick?
In the matrix exponential case, it seems like you have this tunable parameter, which is the time frame that you're using to make each of those STMs that you're stacking.
Yep.
Are you able to sort of approach the performance of the numerical case by tweaking that down, and does it still have a better runtime, or do you eventually kind of overshoot that runtime when you crank that?
We don't know
down?
yet, but it's something we're going to do.
Okay, cool.
Yeah, that is one of the big things, right, is that this choice of time step. Also affects, so for example, the reason why the computational advantage isn't so great here is because this is a much longer control window than being considered by the other reconfiguration. And as you might think, with this approach, the longer you propagate and given a fixed time step here, the longer it's going to take to stack these matrices, because it's almost an exponential relationship there with runtime. So that is something else that needs to be addressed and looked at, but we're at the abstract stage. So haven't gotten there yet.
Can't you use like a transformation matrix so that like you can kind of correct like the sort of like state at t0 to the like T1, if that makes sense. I think like in ROE, like you basically ROE itself is like a time varying system, but I believe like they correct the state transition matrix by like multiplying like some like matrix like at the T0, and then like making some like sort of like other transformation matrix which is a function of T, and then by stacking the inverse of it from like left side, and then like having a like multiplication of like some other like, and then like you can sort of like approximate probably better than like just simply multiplying and stacking like the state transition matrix, I think.
Matthew, this is something I showed in our work where you can introduce it's a Floquet theory. Basically, you introduce a transformation of the state to get a linear time invariant system. Then you find the STM for that linear time invariant system, and then you apply the inverse of that transformation to get to the STM of the time variant.
Yeah.
But we have to be lucky to find that transformation to get from the linear time variant to the linear time invariant system. But I don't think anybody has looked at that approach here.
Yeah. It's more things that need to
That would be
looked further
interesting to
into.
explore,
Yeah.
because once we have an analytical form of the STM, then all the other tools open up. You can find
Everything
cross-form
follows.
solutions, and that's it.
All right. If anyone has any other questions, everything that's left is still just conclusions. But yeah, I think you guys got it. Reachable set theory is cool. Yeah.
Thank you very much.
Thank you.